The rise of augmented reality is giving users more control over their presence in the real world by allowing users to interact with their environments. Being able to create and share virtual 3D scans allows for wider seamless integration of virtual objects into physical surroundings. Now picture this. You're travelling around the world and find a monument. Desperate to share this with your friends and family back home, you get your phone out to try your hand at scanning to produce a recreation for them. But you hesitate. How do you start? How do you get the system to recognise what you want to scan? How do you know you're doing well, and how do you avoid bumping into people, or even feeling awkward while scanning? If you've tried 3D scanning on any modern commercial scanning apps before, like Wayfarer or Snap's custom landmark maker, you may have asked these exact same questions. Whilst you can see the camera view on screen, there isn't any guidance to indicate how well you're doing. The lack of feedback can be disorientating, alienating people from repeating scanning in the future. When there is a high demand in our modern world for quality scans to expand AR's potential, this needs to be solved. So, we set about outlining clear guidance for how to do a complete scan. We explored the need to bridge the gap between users and the act of scanning through evaluation of user experience. Our research went through 3 phases: conceptual design, a pilot study exploring the effect of guidance, and finally, a full user study to compare different guidance approaches. So follow us as we quell your fears and show you step by step how scanning can really be a piece of cake, with the right guidance. First, the system needs a sense of what you're scanning. Previously, systems asked the user to indicate where the subject was and its size. In our pilot study, we experimented with the same approach, placing a virtual object, then adjusting its position, width, and height. This did give users more control over the experience, however a new problem arose. The placement of the object focus began to drift. This proved frustrating. Even when framing the object well, the feedback said otherwise. To overcome this, we designed our landmark tracker, a drift reduction algorithm. In the final study, this ensured continuous re-estimation of the object position using scene segmentation, instead of relying on just the SLAM algorithm. Now all users had to do was tap the screen to indicate what the landmark looked like. So great, you've identified the object. You're on your way to creating your first scan. But now you're concerned about how to get going and make the best scan possible. The quality of a scan is dependent on consistency of 3 things: distance, speed, and point of view. These are all very difficult to maintain and measure by instinct, so we developed guidance features to keep users on track. In our final study, we had 2 differing sensory approaches to each guidance feature. One using visual feedback whilst giving users a view of the meshing overlay of the statue, the other using audio haptic feedback over a blacked out screen. To help users maintain a consistent distance from the object, our system would identify a track around the centre point of the identified object. On our visual application, a blue track was laid before users to follow. Our audio application used music. When a user was on the right track, our music appeared louder and happier. However, if they strayed, the music changed, becoming quieter and distorted. For example, if they got too close, it changed like this. And if they got too far away, it sounded like this. The 2 application types also guided the users to keep the object in camera view. For the visual application, users received text feedback on the screen when their point of view drifted. For the audio haptic application, however, we implemented haptic feedback. The further the object was from view, the stronger the buzzing sensation was for users. The speed users were progressing at was also addressed. Visual users were prompted once again by on-screen text to slow down, and our audio users were alerted by a message played through the headphones.
Slow down, please.
When the users were finished, they received confirmation, either through visual means or by audio.
You did it!
Then the users could view their object recreation, and that's it. Now you can scan to your heart's content. But now you may be wondering, will guidance really help me? And if it does, which method will aid me best? Let's address this. Our pilot study found our initial guidance system to be intuitive and more enjoyable when compared to a pre-existing scanning application that gives no guidance. Users felt more aware of their surroundings and even found our audio prompts rewarding. Having proven guidance to be beneficial, we set about determining how to deliver guidance most effectively. Our final study was conducted in busy central London with 50 users. To evaluate the 2 guidance methods provided, we looked at user engagement and stress, as well as the accuracy of their scan. We measured these using 3 tools. Users completed surveys before and after scanning, as well as a final demographic survey, and we measured their heart rate and the quality of the construction their scan created. Our results indicate our audio haptic users had higher levels of engagement, finding the experience more absorbing compared to our visual users. Usability saw the same pattern, and the same was seen for reward. Overall, it seems our audio haptic users had a better experience. We also asked users to report the stresses they faced during scanning. The top 2 concerns were navigating crowds and fear of thieves. However, the 2 leading social stresses gave new insight. Our audio users less often reported concerns about privacy of the public and social perception, indicating audio haptic guidance reduces fear of social judgment, potentially encouraging more people to feel comfortable scanning in public. Our landmark tracker algorithm also proved to reduce the proportion of users who experienced drift by 65%. We numerically compared users' scans by aligning them to a high-quality reconstruction of the Agatha Christie statue and calculating chamfer distances and F-scores. We found that reconstructions from audio haptic guided users were more accurate than visual user reconstructions on every metric, with the chamfer distance being significantly better for the audio haptic condition. To conclude, we provided guidance that gave users a better experience when scanning. Our audio haptic feedback proved more engaging and rewarding to users than visual, and audio-guided users also produced higher quality reconstructions. Drift was dramatically reduced thanks to the help of our algorithm. With our findings implemented, the world of scanning becomes more accessible and enjoyable for all. Now go out there and scan like a pro.